We are diving straight into a huge debate happening right now in artificial intelligence.
A really big one.
Yeah, on one side, you have the technology that's just consuming all the headlines, large language models, LLMs, the current AI gold rush. But then, standing against that massive trend, you have a true giant of the field, Turing Award winner Richard Sutton, who basically argues the entire approach is, well, fundamentally wrong.
It's a serious claim, and we really have to put it in context for you. Sutton isn't just some academic with an opinion. He is, the inventor of these foundational principles in reinforcement learning, or RL. He's the man behind things like temporal difference learning, policy gradient methods, the stuff that underpins the big successes from DeepMind and others.
So when the winner of the Nobel Prize for Computer Science says the prevailing fashion is a dead end, we probably ought to pay attention. So the conflict is clear. LLMs are all about mimicking human intelligence, right? Predicting what people would say. Sutton's work, reinforcement learning, is about achieving goals by understanding the world. And, I think this is the key, learning what to do.
That's it.
Our mission today is to really get into why Sutton believes LLMs are built on the wrong premise for ever achieving true intelligence.
I mean, in any tech boom, we risk losing sight of first principles. And for Sutton, RL is basic AI. It's the foundation. The whole conflict really boils down to this. Are we trying to build a machine that describes the world based on human text? Or are we trying to build an agent that learns by actually acting in the world?
Okay, let's unpack that foundational difference. How does RL define intelligence, and how is that so different from the way we train an LLM?
Well, for an RL agent, intelligence is the ability to understand your environment and learn purely from experience. The core loop is you take an action, you see what happens, the world reacts, and that's what you learn from. It's this active, exploratory relationship with reality.
It's a feedback loop.
A constant feedback loop. LLMs, on the other hand, are trained on this massive but static pile of human data. The data is inherently passive. It's always, here's a situation, and here's what a human wrote next. So the model is learning imitation. It's learning to do what people did, not learning why an action causes a certain outcome.
Okay, but I have to push back a little here, because this is the common assumption, right?
What for?
LLM proponents say, look, this thing can describe how to fix a car engine, the physics of a black hole, the history of Rome, flawlessly. Surely, to do that, to synthesize trillions of tokens so accurately, the model must have built a deep, robust world model inside. Isn't language itself, the ultimate compression of our knowledge about the world?
That's a great question, and it's the heart of the debate. But Sutton's retort here is really sharp. He says, you are not building a model of the world. You are only mimicking people that have a model of the world. Think about your car engine example. The LLM can generate the text. Turn the bolt clockwise with a 15-millimeter wrench. But it has no idea if the wrench is greasy or if the bolt is rusted and about to snap off.
Because the RL agent is the one actually holding the wrench.
Exactly. The RL agent's prediction is, if I apply this much torque, will the bolt turn or will it break? The LLM's prediction is only what word comes next. Yeah. What LLMs predict is what a person would say, not what will happen in the real world. Sutton ties this right back to Alan Turing, who wanted a machine that learns from direct experience, not just by reading our notes.
That separation predicting human words versus predicting world outcomes, that's absolutely crucial. And I guess that this is where the idea of a goal comes in. Sutton argues that without a real goal, you don't even have true intelligence.
He takes a very classical view here. She cites John McCarthy, one of the founders of AI, who defined intelligence as the computational part of the ability to achieve goals. If you don't have a goal, you don't really need a world model because there's nothing for that model to, optimize for.
So if the machine is just generating text, what happens to the idea of truth or knowledge? Why do LLMs fail this goal test?
They fail because in the LLM framework, there's no inherent definition of actual knowledge. There's no such thing as a good action or a bad action. There's no ground truth.
No link to reality.
Right. If the model solves a complex math problem, it gets no feedback from the universe on whether it's actually right. It only gets feedback on whether its answer looks like an answer a human wrote down somewhere in its training data. And this is in stark contrast to RL. In RL, there is a ground truth, and it's simple. Reward. The right thing to do is whatever gets you that reward.
So the reward provides an empirical check.
A constant check on its beliefs. If the agent thinks path A is better, but it gets more reward from path B, it has to fundamentally adjust its understanding of the world. LLMs just don't have that mechanism.
But wait, the common counterargument is that LLMs do have a goal. Next token prediction. Isn't that a goal?
Sutton's take on this is that next token prediction is not a substantive goal. It's not substantive because it lacks agency. The analogy he uses is like a really skilled movie critic. The critic can perfectly predict the next plot twist in a film, and they might be happy they were right, but their prediction has zero influence on the film itself. The film is already made.
Ah, so the tokens just come at the system. Predicting them accurately doesn't change anything in the world. The system is totally passive.
Precisely. He says the system is just sitting there predicting and being happy with itself that it's predicting accurately. But it's a passenger watching the world go by, not the driver who can actually steer.
That lack of agency brings us to what feels like the ultimate test of a true world model, the ability to be surprised and to adjust.
Exactly. A true world model lets you predict what will happen if you do something. And if you take an action and something totally unexpected happens, your prediction fails. That surprise is the most valuable learning moment possible. The system is forced to make a fundamental adjustment to its internal physics, its understanding of how things work.
So how does that apply to LLMs?
Well, even when they do impressive things like chain of thought reasoning to solve a math problem, they don't have this capability. If they generate a result that contradicts the real world, say they predict a chemical reaction that fails in a lab, they can't be genuinely surprised. They're only predicting text strings, not physical states. So they won't make changes based on that unexpected event out in reality.
Okay, that clarifies it. LLM prediction is about what the system should say. It is not a prediction of what the world will give back in response.
And without that feedback loop, you can't be surprised by the world. This all ties back to a concept Sutton has been championing for years, the bitter lesson.
Right, the idea that powerful but general methods like search and learning always end up beating methods that rely on packing in a lot of human knowledge.
Exactly. We saw it play out with symbolic AI in the 80s and 90s. Experts tried to hand code rules for intelligence, and then brute force systems like Deep Blue just won.
They just scaled better?
They scale better. LLMs show fantastic scaling, they use massive computation, but Sutton's critique is that they also rely on putting in tons of human knowledge, the entire internet. This reliance on uncontrolled data makes them unreliable for things like scientific discovery, where you need to know where your knowledge came from. He predicts that systems that learn purely from experience RL systems will eventually supersede LLMs, proving the bitter lesson true all over again.
So if the LLM approach is starting from the wrong place, what does the architecture of a truly scalable continual learning system actually look like?
The RL paradigm is all about this dynamic, endless loop. Sensation, action, reward. The whole mission is to constantly tweak your action to maximize your reward. What you learn, your knowledge, is a set of statements about that stream. If I do X, Y will happen. And because this knowledge is about the world, you can constantly test it against reality.
That sounds incredibly rich, but how is that knowledge actually structured? It's not just a big list of actions and rewards, is it?
No, not at all. Sutton details 4 essential parts of a robust learning agent. We can use the analogy of running a company to make it clearer.
Okay, let's do that.
The first part is the policy. That's your CEO. It's the immediate decision maker. What should I do right now in this situation?
Simple enough. But what about long-term thinking?
That's the value function.
Right.
And this is where RL gets really powerful. The value function is like the CFO. It predicts the long-term aggregated outcome, and it learns this mainly through temporal difference learning, or TD learning.
Let's define TD learning for a second, because it's a huge concept.
It is. TD learning is basically how an AI learns delayed gratification. It learns the value of being in a certain state, even if the final reward for that state won't show up for a long, long time. If your goal is a 10-year startup exit, the value function figures out if making a good hire today makes that exit more likely later. It reinforces all the little intermediate steps.
That makes the whole thing feel much more, well, mammalian. It's anticipating the future consequences of what you're doing right now.
Precisely. The third part is perception. This is your market research department. It builds the agent's picture of its current state. Where are we now? What's the competition doing? And the fourth part, the key differentiator from LLMs, is the transition model of the world. This is the internal physics engine, the belief about what will happen if you take an action. If we launch this product, how will the market react? And this model is learned richly from all the sensation you receive. The reward is just a tiny guiding signal. Most of the worldview is built just from watching what happens.
It's just remarkable, isn't it? The things AIs currently struggle with, this robust, continual learning that lets you adjust to a messy new environment, is something that all mammals and even insects can do.
It's Moravec's paradox all over again. We've built systems that can master the math Olympiads, things almost no animal can do, yet they struggle with the basic learning an infant masters in its first year.
Sensing, acting, and adjusting based on the outcome.
Exactly. The LLM approach, by relying on text, has basically tried to skip that biological experiential route to intelligence.
So connecting this all back, why does Sutton think the world is just too big for the LLM approach to ever fully work?
Because the world is too huge, too detailed, and filled with too many local oddities, like the specific culture of one client or the unique physics of one machine on a factory floor. You can't teach all of that in advance. The dream of LLMs is that you can teach the agent everything up front by feeding it all human text. Sutton says that's just impossible. You need online continual learning to handle the infinite small details that define reality.
That makes the LLM boom sound like a massive, very sophisticated detour.
Sutton certainly sees it as a transition stage. He looks at this in almost cosmic terms. He suggests humanity is moving from an age of replicators, where we make children without fully understanding intelligence, to an age of designed entities, AIs that we build and understand. He sees this as one of the four great stages of the universe, right up there with the formation of dust, stars, and life itself.
And he positions himself as a classicist in all this.
Absolutely. He argues the history of AI always proves that weak methods, simple principles like search and learning, win out over strong methods that try to hardcode human knowledge. He points out that the success of AlphaGo and AlphaZero, while it was shocking to the public, was really just a massive scaling up of techniques like TD Gammon that were already around in the 90s. The principles of experiential learning just won again.
That brings us to a really fascinating future application of this bitter lesson. If you follow this logic forward, Sutton suggests it might even apply to post-AGI systems. If we had a super-intelligent AI researcher, how should it proceed? Should it use its own compute to become even smarter itself? Or should it spawn off countless copies to learn different things and report back?
It raises this vital question about how a digital mind should grow. Spawning copies and reintegrating their knowledge seems incredibly efficient, right? But Sutton raises the danger of what he calls digital corruption.
Corruption. What kind of corruption would threaten an AGI?
If you try to pull in external information or the knowledge learned by a copyback into your central mind, you risk contamination. Those billions of bits could contain hidden, misaligned goals or policies learned in some uncontrolled environment. Integrating that knowledge could subtly warp the original AI's values, leading to its destruction or misalignment instead of just making it smarter.
That is a truly provocative thought for you to mull over. We assume knowledge is always a good thing, always additive. But Sutton suggests the next bitter lesson might be that integrating external knowledge is catastrophically risky, that true learning has to remain self-contained, active, and continually grounded in experience. Something to think about the next time you ask an LLM for an answer.